Scientists have been searching for something on Neptune for 30 years. Voyager 2 hinted at it back in 1989, but nobody could prove it existed. Then James Webb did the impossible. It saw something glowing in Neptune's upper atmosphere that shouldn't be there. And what it found has changed everything we thought we knew about how this distant planet actually works. On a cold June day in 2023, nearly 2 billion miles from Earth, a telescope hovering at the edge of space pointed its infrared eyes at a distant blue world and finally solved a mystery that had puzzled astronomers for more than 3 decades. This discovery represents one of the most significant breakthroughs in planetary science in recent years, and to understand its significance, we need to understand what auroras are and why they matter so much to scientists studying planets throughout our solar system. Auroras are perhaps some of the most beautiful phenomena in the solar system. They are created when charged particles from the sun collide with a planet's atmosphere. These particles travel along the planet's magnetic field lines, spiraling down toward the regions where the magnetic field converges into the planet. When they strike atmospheric molecules, they transfer their energy, exciting the molecules into higher energy states. When those molecules release this excess energy, they emit light, brilliant, shimmering light that creates the dancing curtains we call auroras. On Earth, auroras occur predominantly near the poles because Earth's magnetic field lines converge toward the north and south magnetic poles. But on other planets, the geometry is completely different, and the auroras appear in different locations depending on the unique configuration of each planet's magnetic field. This fundamental principle of planetary magnetism would become crucial to understanding why Neptune's auroras were so difficult to find. Neptune is one of the most remote places in our solar system. It orbits so far from the sun that sunlight takes more than 4 hours to reach it. The planet itself is a massive ice giant, swirling with dark storms that appear and vanish without warning, surrounded by faint rings and a collection of strange moons. Its diameter is about 4 times larger than Earth's diameter, yet it remains invisible to the naked eye because it is so incredibly distant. Neptune orbits in a region of space that is cold, dark, and inhospitable to any form of life as we know it. Only one spacecraft has ever visited Neptune up close. That was Voyager 2, which conducted a brief flyby on August 25th, 1989. During those few precious hours, as Voyager 2 raced past the ice giant at 30,000 miles per hour, its instruments gathered a wealth of data about Neptune's atmosphere, its magnetic field, its rings, and its mysterious moon system. The data was revolutionary at the time, revealing Neptune to be a world far more complex and dynamic than scientists had anticipated. But there was something strange in that Voyager 2 data that scientists could not quite explain. The spacecraft's instruments hinted at auroras on Neptune, those beautiful shimmering lights that occur when charged particles from the sun slam into a planet's upper atmosphere. On Jupiter, Saturn, and Uranus, scientists had learned to recognize a specific molecular signature associated with auroras. They were looking for something called trihydrogen cation, or H3 positive. This molecule forms when energetic charged particles ionize hydrogen molecules in a planet's atmosphere. H3 positive is significant because it is one of the most abundant ions in the entire universe. When H3 positive forms, it emits light at specific infrared wavelengths. This infrared emission can be detected and analyzed by sensitive instruments. Scientists had learned that wherever they detected H3 positive emissions on the gas giants, they were detecting auroral activity. The molecular signature of H3 positive had become the calling card of planetary auroras. Voyager 2's data suggested that H3 positive might be present in Neptune's upper atmosphere, but the signals were incredibly faint and confusing. Nobody could definitively say that Voyager 2 had detected auroras at Neptune. The data was ambiguous. Scientists were tantalizing close to confirming auroras at Neptune, but that confirmation remained just out of reach. For the next 34 years, astronomers tried everything to confirm what Voyager 2 had suggested. They pointed the most powerful ground-based telescopes on Earth toward Neptune, including the Keck Observatory in Hawaii, which has one of the largest telescope mirrors in the world, and the NASA Infrared Telescope Facility, also located in Hawaii. Scientists knew exactly what to look for. They knew the specific infrared wavelengths where H3 positive glows. They had sensitive detectors. They had the best optical and infrared technology available. Yet despite all these advantages, despite decades of dedicated observation campaigns, despite years of effort, they could not detect auroras at Neptune. It was as if Neptune was deliberately hiding its auroras from human observation. The failure to detect Neptune's auroras was deeply puzzling because theoretical models predicted that Neptune absolutely should have them. The mathematics said so. The physics said so. Neptune's atmosphere is made primarily of hydrogen and helium, just like Jupiter and Saturn. These are the exact same gases where auroras glow so brilliantly. Neptune has a magnetic field that should interact with solar wind particles in the same way that other gas giants do. Every prediction suggested that Neptune should be glowing with auroras just as brightly as its planetary siblings. But somehow, these lights remained invisible. It was one of the most frustrating mysteries in planetary science. Scientists began to wonder if something was fundamentally different about Neptune. Maybe the planet's auroras were so faint that they could never be detected from Earth, no matter how powerful the telescope. Maybe something about Neptune's atmosphere prevented the formation of H3 positive molecules altogether. Maybe Neptune's magnetic field configuration was so different from other planets that auroras simply could not form at all. Maybe auroras occurred on Neptune only briefly and rarely during special circumstances. The mystery deepened with each failed attempt to observe them, and the puzzle became increasingly urgent as decades passed without resolution. Then, in October 2021, NASA launched the James Webb Space Telescope. Webb is the most powerful space-based telescope ever built, a technological marvel that represents decades of engineering innovation and billions of dollars of investment. The telescope orbits the Sun at a location called the Second Lagrange Point, or L2, nearly 1.5 million kilometers from Earth. At this location, the gravitational pull of the Sun and Earth balance each other perfectly, allowing Webb to maintain a stable orbit with minimal fuel consumption. Webb's primary mirror is made of hexagonal segments of beryllium coated with gold. The hexagonal segments fit together to create an effective mirror diameter of 6.5 meters. Gold was chosen because it is highly reflective in infrared wavelengths and does not degrade when exposed to the vacuum of space. Webb's infrared capabilities are extraordinary. The telescope can see light with wavelengths between 0.6 and 28 micrometers, well beyond what the human eye can perceive. Webb was designed to look at distant galaxies, to peer back toward the beginning of the universe itself, to study exoplanets orbiting other stars, but it could also be used to study objects closer to home, including planets in our own solar system. Scientists quickly realized that if any instrument had a chance of detecting Neptune's elusive auroras after decades of failed attempts, it would be Webb. The telescope's infrared sensitivity and spectroscopic capabilities were simply in a different league from any previous instrument. In June of 2023, nearly 3 years after Webb began its mission, astronomers pointed the telescope toward Neptune. Specifically, they used Webb's near-infrared spectrograph, an instrument of extraordinary precision and sensitivity. The spectrograph is capable of detecting individual photons of infrared light reflecting or glowing from distant objects. The spectrograph works by breaking down light into its component wavelengths, similar to how a prism creates a rainbow from white light. By analyzing the specific wavelengths of light coming from Neptune, scientists could identify the chemical signatures of different molecules in the planet's atmosphere. The team collected data from 2 different viewing angles of Neptune on June 22, 2023, observing different hemispheres of the planet to capture as much information as possible. What happened next shocked the scientific community. When researchers analyzed the data from Webb's near-infrared spectrograph, they found an extremely prominent emission line. This emission line corresponded perfectly to trihydrogen cation, H3 positive. For the first time in human history, scientists had definitive confirmation that Neptune possesses auroras. The search that had lasted 34 years was finally over. The glow appeared in the infrared images as cyan-colored splotches scattered across the planet. But the more scientists studied these images, the more confused they became. The auroras on Neptune were not where they were supposed to be. On Earth, auroras occur near the north and south magnetic poles, creating the famous northern lights and southern lights that fascinate observers at high latitudes. On Jupiter, auroras glow brilliantly at the poles in shades of red and blue. On Saturn, the same pattern holds true. The auroras cluster around the rotational poles. But Neptune's auroras were different. Instead of appearing near the planet's north and south poles, they glowed at the planet's middle latitudes, roughly where South America sits on Earth. It was as if someone had taken the rules of planetary magnetism and completely rewritten them. The reason for this bizarre location traces back to something extraordinary that Voyager 2 discovered in 1989. Neptune has the strangest magnetic field of any planet in our solar system. The planet's magnetic field is tilted by 47 degrees relative to its rotation axis. To put that in perspective, Earth's magnetic field is tilted by about 11 degrees, which is why magnetic north is not at the same location as geographic north. Jupiter's magnetic field is nearly aligned with its rotation axis, tilted by only about 3 degrees. But Neptune's magnetic field is tilted almost at a right angle to its rotation axis. Even more strangely, Neptune's magnetic field is not centered at the planet's core. It is offset from the center by more than half a planetary radius. If Neptune were the size of a basketball, the center of its magnetic field would be displaced several inches from the center of the basketball. Scientists still do not fully understand why Neptune's magnetic field has this bizarre configuration. Some researchers believe it may have to do with the exotic state of water in Neptune's interior, where the extreme pressures and temperatures create something called superionic ice, a phase of water that does not exist anywhere on Earth. This exotic ice phase may generate Neptune's irregular magnetism in ways that scientists are still working to understand completely. Whatever the cause, the effect is dramatic and unmistakable. The magnetic field lines that normally converge toward the poles instead converge toward the planet's middle latitudes. Since auroras form where magnetic field lines funnel charged particles into the atmosphere, Neptune's auroras glow in the middle of the planet rather than at the poles. The geometry is completely different from what scientists expected. The implications are profound. It means that ice giants can have dramatically different magnetospheric configurations from gas giants. It means that planetary magnetism is far more complex and varied than previously understood. It means that future observations of Uranus, which also has a severely tilted and offset magnetic field, could reveal equally unusual auroral configurations. Scientists were not just shocked by where the auroras appeared. They were deeply surprised that the auroras appeared at all. And there was another mystery hiding in the data that would prove equally illuminating. When researchers measured the temperature of Neptune's upper atmosphere using Webb, they discovered something truly astonishing. Since Voyager 2's visit in 1989, Neptune's upper atmosphere had cooled by several hundred degrees Fahrenheit. The temperature in 2023 was just over half of what it had been 34 years earlier. This massive cooling represented a dramatic change in Neptune's thermal balance. This cooling held a crucial clue to why Neptune's auroras had remained hidden for so long. The research team was led by Henrik Mellon of Northumbria University, who was conducting research on Neptune while working at the University of Leicester. Mellon stated that he was absolutely astonished to find that Neptune's upper atmosphere had cooled by several hundred degrees. The implications were profound and far-reaching. Cooler gas emits less light. This is a fundamental principle of physics. When gas is heated, its molecules move faster and have more energy. When they emit light, that light is brighter and more intense. But when gas cools down, its molecules move more slowly and have less energy. When they emit light, that light is dimmer and fainter. A cooler aurora appears much fainter and more difficult to detect. Scientists realized that this cooling was likely the primary reason why decades of Earth-based observations had failed to detect Neptune's auroras. The auroras were there all along, glowing in the infrared, creating the telltale H3 positive signature that scientists knew how to recognize. They were just too faint to see with conventional telescopes. It took Webb's extraordinary sensitivity to pierce through the darkness and confirm what scientists had suspected, but could not prove for more than 3 decades. The discovery demonstrated that sometimes the tools we have available determine what we can and cannot observe in the universe. But why had Neptune's upper atmosphere cooled so dramatically over 3 decades? This is a question that continues to puzzle planetary scientists and generate new research initiatives. One intriguing possibility involves Neptune's distant orbit around the Sun and the planet's slow progression through its orbital seasons. Neptune takes 165 Earth years to complete a single orbit around the Sun. This means that Neptune experiences seasons that last approximately 40 years each. Voyager 2 visited Neptune during a period when one hemisphere was tilted heavily toward the distant Sun, conditions called southern solstice. Since that encounter in 1989, more than 3 decades have passed, and Neptune has moved significantly along its orbital path. By 2023, the planet was approaching an equinox when the Sun appeared more directly above the planet's equator. Perhaps this dramatic shift from solstice to equinox conditions was causing the planet's upper atmosphere to cool as the seasonal distribution of solar heating changed. Another fascinating possibility involves the solar cycle. The Sun's activity varies over approximately 11-year cycles. During solar maximum, the Sun emits more radiation and more energetic particles that bombard planetary atmospheres. During solar minimum, the Sun is quieter and less active. The amount of energy the Sun sends to Neptune's upper atmosphere could profoundly influence its temperature and thermal balance. Scientists believe that the cooling trend might be related to a combination of seasonal effects and solar cycle variations working together to cool Neptune's upper atmosphere. The discovery of Neptune's auroras had profound implications that extended far beyond Neptune itself. It confirmed that auroras are a universal phenomenon in our solar system, appearing on all of the giant planets. Every giant planet, Jupiter, Saturn, Uranus, and now Neptune, experiences auroras. These shimmering lights are not rare or special events occurring only under unusual circumstances. They are fundamental features of how planetary magnetospheres interact with the solar wind. But Neptune's auroras also demonstrated that planetary systems can be far more complex and diverse than scientists had previously imagined in their theoretical models. Neptune breaks the rules. Its magnetic field behaves differently from all other planets. Its auroras appear in unexpected places, driven by the unusual geometry of its magnetosphere. Its atmosphere undergoes dramatic changes over decades, cooling in ways that perplex researchers. The ice giant refuses to conform to our simple models and theories, forcing scientists to reconsider and revise their understanding of how planets work and how magnetic fields function in diverse planetary environments. The research team that made this groundbreaking discovery was led by Henrik Mellon and included scientists from multiple prestigious institutions across the world. Heidi Hamel of the Association of Universities for Research in Astronomy was the principal investigator for the Guaranteed Time Observation Program through which the data were obtained. Hamel is a renowned expert on Neptune and has spent her career studying this distant ice giant. Lee Fletcher of the University of Leicester, a specialist in infrared planetary observations, played a crucial role in the research and interpretation of the results. Stephanie Milam from NASA's Goddard Space Flight Center contributed her expertise in spectroscopy and atmospheric chemistry. The team's findings were published in the prestigious journal Nature Astronomy in March of 2020, less than a year after the observations were conducted. The paper detailed not only the confirmation of Neptune's auroras, but also the temperature measurements, the spatial distribution of the auroras, and the implications for understanding Neptune's atmosphere and magnetosphere. The rapid publication reflected the significance of the discovery and the quality of the research. Within months of publication, the discovery had captured the imagination of scientists, media outlets, and the general public alike. It showed that even with instruments as advanced as the James Webb Space Telescope, the solar system still held surprises. Neptune, having been visited by just one spacecraft in the previous 3.5 decades, remained largely mysterious. The Aurora discovery opened up new avenues for understanding this distant world. It demonstrated that ice giants deserve as much scientific attention as gas giants like Jupiter and Saturn. It highlighted the importance of infrared observations for studying planetary atmospheres and magnetospheres. It showed that technological advancement can solve mysteries that seemed intractable just years before. The discovery of Neptune's auroras also immediately opened up new questions about the other ice giant, Uranus. Like Neptune, Uranus has a magnetic field that is dramatically tilted from its rotation axis, but Uranus is tilted even more extremely than Neptune. Uranus is tilted by 98 degrees, meaning it is nearly perpendicular to the planet's rotation. In fact, Uranus rotates on its side, with its poles pointing nearly toward and away from the Sun. Scientists immediately began planning observations of Uranus with the James Webb Space Telescope to determine if it also has auroras similar to Neptune's. If Uranus does have auroras, they would appear in even more unusual locations, driven by the planet's extreme magnetic field configuration. These observations could provide a unique window into the processes that govern auroras on ice giants and how diverse magnetic field geometries affect auroral displays. The investigation of Uranus's auroras would build directly on the success of the Neptune observations. Beyond the immediate scientific findings, the discovery of Neptune's auroras highlighted the importance of the James Webb Space Telescope for solar system science. Webb was designed and built primarily to study distant galaxies and exoplanets, to look deep into space and far back in time toward the era when the first galaxies formed. But the telescope's infrared sensitivity and spectroscopic capabilities make it equally valuable for studying objects closer to home, including planets, moons, and smaller bodies in our own solar system. Webb can see details that would be impossible to detect from Earth-based observatories, particularly in the infrared. Webb can observe in infrared wavelengths that are completely blocked by Earth's atmosphere, which is opaque to most infrared radiation. These capabilities make Webb an essential tool for planetary scientists seeking to understand the atmospheres, compositions, dynamics, and magnetic interactions of the giant planets.